Good evening. Today we will discuss multivariate inferential statistics. We will start with single population mean vector and then we will go for two population mean vectors. Now, under single population mean vector, these are the items we will be covering today. One is multivariate central limit theorem, Hotelling t-square distribution, inference about single population mean vector, under this confidence region, simultaneous confidence intervals, hypothesis testing followed by references. Now, let us think that you are sampling from multivariate normal distribution, that X is multivariate normal where the population parameters are mu, which is mu 1, mu 2, it is a mu vector p cross 1, and your covariance matrix is p cross p, and you all know that what is the elements, that is sigma 1 1, sigma 1 2, like sigma 1 p, sigma 1 2, sigma 2 2, sigma 2 p, like this, sigma 1 p, sigma 2 p, sigma p p. This is what is your population. When you sample from the population, for example a sample of size n, then you compute sample statistics like x bar, which is again a p variable vector, x 1 bar, x 2 bar, like this, x p bar, and you also compute that covariance matrix, which is S 11, S 12, S 1p, S 12, S 22, like S 2p, and followed by this S 1p, S 2p dot 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 S p p, p cross p. What formula you have used earlier? You have seen already, you have seen that you have used this formula to calculate this. If your data matrix is A x n cross p, then what you have used here, you have used this one is 1 by n, then x transpose, and you are creating a unit vector here, where 1 is 1 1 1, like this, 1 n cross 1. For sample covariance, you have computed like this, that is x minus your, it will be p cross p. So, 1 dot x bar transpose, then transpose followed by x minus 1 dot x bar transpose. This is the formula you have used. Fine. Now, when we talk about the inferential statistics, you have seen in univariate case also that we talk about the distribution of the statistic of interest. For example, you may be interested to know what is the distribution of x bar. Similarly, what is the distribution of S? Now, x bar that follows normal distribution, that is multivariate normal with p variables mu sigma by n, and S follows Wishart distribution, Wishart distribution with n minus 1 degrees of freedom. This is a complex distribution, Wishart distribution. We will not talk anything about this Wishart distribution henceforth. Okay. Now, then the another issue what you have seen in the univariate case also, that is central limit theorem. Now, central limit theorem for multivariate data, for multivariate random variable x bar. What will be this? Here you have seen that square root of x bar minus mu, that follows multivariate normal with 0 mean vector 0 and that covariance matrix sigma. Last class you have seen, some of you have seen, not all, this one, and also we have seen that in x bar minus mu transpose S inverse x bar minus mu, this follows your chi-square distribution. That is what multivariate CLT, multivariate central limit theorem, multivariate central limit theorem. This second part, that in x bar minus mu, S inverse x bar minus mu, that follows chi-square distribution provided n minus p greater than equal to 40, large sample, that is large sample. Okay. Now, what will happen when your sample size is small? So, you go for small sample. Small sample here we are saying that n minus p less than 40. This I have seen in the book by Young and one more professor is there, that applied multivariate modeling in quality management. This is the what I can say when you say it is small sample less than equal to 40. Okay. Now, let us see how do we develop this one, the distribution for the required statistics for x bar when your sample size is small. What we have seen earlier, that way in univariate case, when your sample size is small, you have used T distribution, T equal to x bar minus mu by S by root n. This x bar is the mean, sample mean, and mu is the population mean, S is sample standard deviation, n is the sample size. Now, I want to see what will be its multivariate counterpart. X bar will no longer be your scalar quantity, it will be x bar. Mu also will be a vector quantity, and S will be replaced by that this S, and n will be remain n. That is the case. Okay. If you rewrite this, what you will write, that T equal to x bar minus mu, then here we write square root of n, then S to the power minus 1. Okay. Now, if you make T square, what you will get? N x bar minus mu S square to the power minus 1 x bar minus mu. Now, we like the multivariate normal distribution we developed using univariate normal distribution. Here also we will use the same formulation, similar formulation. So, instead of this T square, we will write capital T square, which is known as Hotelling T square. Hotelling's T square. So, this will be written like this: n x bar minus mu transpose, then this will become a S. So, what we say here, that S, that counterpart will be taking at capital S, basically this is a square in terms of variance. So, S inverse x bar minus mu, and Hotelling has proved that this quantity will follow n minus 1 p by n minus p f p n minus p, that is f distribution. It will follow f distribution. So, when you take small sample size, you will find that this is the statistics. This statistic is of importance now, and the derivation of this t square is this, and it will follow this distribution. Okay. Now, see the problem what I have solved in another class. Again I want to solve it here, and it may be repetition for some of you, but for others it is not that. So, a random sample with size n equal to 20 were collected from a bivariate normal process. The sample mean vector and covariance matrix are given below. What is this? X bar is 10, 20, that is the mean vector, and covariance matrix is S, that is 40, minus 50, minus 50 and 100. We want what will be the value of Hotelling t square, that statistic value. Answer is this 1.33 10 minus mu 1 to the power square, like this. So, for some of you who are not gone through that computation, for you please see what is this t square is n x bar minus mu transpose S inverse x bar minus mu. What is your x bar? X bar given 10, 20. What is your mu? Mu is mu 1 and mu 2, because it is a bivariate case. What is S given? S given 40, minus 50, minus 50, 100. What you require to compute? You require to compute first x bar minus mu, which is 10, 20 minus mu 1, mu 2. This is nothing but 10 minus mu 1, 20 minus mu 2, which will be a 2 cross 1 vector. Then you require to compute S inverse. S inverse is 1 by determinant of S adjoint of S. Now, you all know that adjoint of S is that I told you in one class. So, this was is this, that you find out here that cofactor transpose of cofactor matrix, that you want to find out. Anyhow, we will see this. So, determinant of S is determinant of 40 minus 50 minus 50 100. This will be 40 into 100 minus 50 into minus 50. So, this will be 4000 minus 2500, which will be 1500. Okay. Now, you see the transpose of cofactor of S. So, S is 40 minus 50 minus 50 and 100. When you find out the cofactors for this particular element, you have to cross that particular row and column. So, ultimately what you get here, minus 1 to the power I equal to 1, j equal to 1, then what is remaining, that is 100. In the same manner, you will go with and you will find out here minus 1 to the power row 1 column 2, then what is remaining, if I go by this, remaining will be this, and here minus 1 2 plus 1, that remaining portion is this, and here minus 1 2 plus 2, remaining portion will be 40. The resultant quantity will be 100, then 50, then 50 and 40. Now, if you take the transpose, you will get the same thing, because it is a square symmetric matrix, you will get the same thing. So, S inverse will be 1 by 1500 into this. This will be your S inverse. Once you know S inverse, what you require to compute now? You want to compute now this one. So, I can see this one first. If I write S inverse x bar minus mu, then this is nothing but 1 by 1500 into 100, 50, 50, 40, and your x bar minus mu is 10 minus mu 1, 20 minus mu 2, 10 minus mu 1, 20 minus mu 2. So, 1 by 1500, this is 2 cross 2 matrix, 2 cross 1 matrix. So, your resultant will be 2 cross 1 matrix. So, 100 into 10 minus mu 1, 100 this into this plus this into this. So, plus 50 into 20 minus mu 2. Then again 50 into this 10 minus mu 1 plus 40 into 20 minus mu 2. So, this is our 2 cross 1. Now, you see T square, n equal to how much? N is 20, and x minus mu transpose will be 10 minus mu 1 and 20 minus mu 2. This will be 1 cross 2 matrix, then into 1 by 1500 into this total quantity 100, 10 minus mu 1 plus 50, 20 minus mu 2 by 50, 10 minus mu 1 plus 40, 20 minus mu 2, 40, 20 minus mu 2. Okay. So, this cut this one to 150, that is 75. So, if I write like this one, this is 1 by 75. Now, you see 1 is to 2 and 2 cross 1. So, you will be getting only one scalar value. So, multiply this into this and this into this. So, your resultant quantity will be 100 into 10 minus mu 1 into 10 minus mu 1, 10 minus mu 1 square, plus 50 into 10 minus mu 1 into 20 minus mu 2. So, this one multiplied with this totality. Then you will find out plus 20 minus mu 2 into 50 into this. So, I can write 50 into 10 minus mu 1, 10 minus mu 1 into 20 minus mu 2 plus you will get 40 into 20 minus mu 2 square. So, the total will be 1 by 75, 100, 10 minus mu 1 square plus 2 into 50 into 10 minus mu 1, 20 minus mu 2 plus 40, 20 minus mu 2 square. Okay. So, I said that this will be 1.33, second one is 1.33, it should be 1.34, it is written, then this one is 0.53. So, resultant quantity is, if I divide this one by 75, that is 1.33 10 minus mu 1 square plus 1.33 10 minus mu 1 into 20 minus mu 2 plus 0.53 20 minus mu 2 square. This type of equation you have seen earlier also. When I ask you to develop the bivariate constant density function, there you have developed this type of equation. It is similar, only difference is this one, and x bar is x S will become sigma, and that was the issue there. Okay. Now, my second question is, what will be the distribution of it? So, distribution means t square follows n minus 1 into p divided by n minus p f p n minus p, that will be your distribution. So, n is 20 minus 1 into p is 2 divided by 20 minus 2, then f p is 2 and 20 minus 2. So, this will be 19 into 2 by 18 f 2 18. So, you can write 19 by 9 f 2 18. Okay. So, you see this slide again. So, our problem is this and your question is this and your answer is this. And in exam prime basically the 2 by 2 matrix will be given, but there is possibility also that you require to compute S given by maybe 3 by 2 matrix. Okay, this is 3 cross 2, this is the data matrix. So, instead of giving you straight away the S, what is required to be given? Required to be given, because you will be getting this only. Initially when you collect data, you will be getting this n cross p, and all other things are to be derived. Okay. This is what is Hotelling t square. What Hotelling t square give you? Hotelling t square gives you a confidence region. Confidence region CR. Okay. That means what we are trying to say, if we follow this one, that t square equal to n x bar minus mu transpose S inverse x bar minus mu, okay, n into this, then we are saying that this is an equation of ellipse when p equal to 2. You have seen earlier when you have derived this something like this, then the equation this one t square equal to this is an equation of ellipse. So, 2 dimensional case it will be equation of ellipse, and you know what will be it in the multi-dimensional situation. What we want to say that this one is like this, the t square value is this will be less than equal to the required probability. What is the probability distribution here? Your probability distribution is this. So, if I say this quantity, so straight away if I write like this, n minus 1 into p by n minus p f p n minus p, the totality I am writing, that probability that this quantity will be less than this, what will be the value? If I put here alpha, 1 minus alpha. Okay. In 2 dimensional case, depending on the alpha, so you will get a depending on, again it all depends on the covariance matrix also, what type of ellipse it will be, but if the variables are independent, then you will be getting ellipse like this. This is what is determined by this quantity. This quantity will determine this, and by 1 minus alpha, if alpha equal to 0.05, that means 95% of the observation will fall on or within the ellipse, on or within the ellipse. If you take alpha equal to 0.01, then your ellipse will be bigger. Reason, this contain 99% of the observations. This is known as confidence ellipse. This is known as confidence ellipse. Where from this ellipse is coming? that you have already seen that this is a quantity which an equation of ellipse when p equal to 2 and when p equal more than 2 it will be equation of ellipsoid. What will be the equation, what will be this equation when all the variables have equal variance? It will be a circle, and for p dimensional scale it will be a sphere. Okay. If all the variables have equal variance, ultimately you get a circle in 2 dimensional and a sphere in spheroid, I think that is the, that will be in the higher dimensional case. Now, we want to understand this confidence ellipse from the original variable point of view, like the x bar for the first variable, that is the mean for the first variable, and x 2 bar is the mean for the second variable. These are all sample mean. We can say okay fine, there are 95% observation within the ellipse or there are 99%, but how do we interpret this? Okay. One of the interpretation could be, suppose you find out the ellipse and then plot in the sense you fix all the points, suppose n points are there. So, you may get points are like this. Suppose you get some one point here, this is one point. So, if I consider the 95% confidence ellipse, then this is an outlier. So, this approach can be used for outlier detection also. Another important issue here is this, you see this figure, this is what we practice in quality control. What he says that there are two dimensions, that x 1 bar and x 2 bar, you see that individual confidence interval and the interval collectively is making one rectangular region A, B, C, D. So, that means some observation falling on here, suppose one observation falling here, based on individual interval it is within the confidence level, but collectively if you see that this is the collective confidence region, then this point is out of the confidence region. So, what is the interpretation then? Interpretation is, if your case is a multivariate case and you go by univariate analysis and accordingly you develop certain intervals, you may find out that the point you are talking about with respect to x 1 bar, this is within the interval, even within with reference to x 2 bar also this will be within the interval, but from their joint density if we consider, this is not within the interval, in the sense within the region, confidence region. That is very important concept. That is why what is suggested that when you infer a multivariate population, you start using the multivariate characteristics of the population. You can go for univariate, but not fast. It is very clearly shown here that if I take this as a quality control example, then what I will find out? I will find out that if I go by univariate that control level UCL and LCL, then a point which is lying here I will accept it as within control, but it is not within control. That will be reflected only when you go by the confidence ellipse in 2 dimensional case. In multidimensional case, confidence ellipsoid. The problem with this confidence ellipse is manifold. What is this? So, you are getting a region, but you cannot make decision based on this region, you only say that okay it is outlier. Okay. For example, it may so happen that the point is here which is outlier or out of control, it is for which variable? Is it out of control for variable x1 or out of control for variable x2? You cannot make any comment based on this confidence interval. In confidence region, that confidence ellipse. Confidence ellipse or ellipsoid will give you idea that yes, one point which is out of the control from quality control point of view, but even other way from simple data analysis point of view you can say that it is an outlier. But why it is outlier, for which variable it is outlier? If you want to find out that, you have to transform from confidence region to confidence interval. What I am trying to say here now? I am telling you that yes, confidence region is the first step, you have to develop it. If you do not develop it, your inference will be faulty. Now, once you have confidence region, suppose one point observation is out of control or outlier, then what is required to be known, that which variable is responsible for this. Then you cannot do anything with this region, you have to go back to confidence interval for each of the variables. That is what is known as simultaneous confidence interval. I will discuss this, but before that I want to do little more on confidence region. What are the steps you have to follow to identify or define confidence region? First you define the population, definitely it is we are considering multivariate normal population, our things become easier. Then you find out the sample statistic, identified appropriate sampling distribution. So, if you do not know the sample statistic and the appropriate statistical distribution, that is the sampling distribution, you cannot go for, even for confidence interval also you are not fit, in the sense you have not enough information to develop confidence interval for univariate case, confidence region for multivariate case. Now, by defined population, what do we mean? Yes? Define population, then obtain sample statistic, then identified appropriate sampling distribution, then develop CR. Okay. Again these are all broad steps, in each step, broad step, there are sub steps also. We will solve one problem for confidence region. By defined population, we are considering three scenarios. Scenario 1, sampling from multivariate normal population with known sigma. That means, you know the covariance matrix for that population. This is a this is basically parameter matrix, covariance parameter matrix. This is my first scenario. Second scenario is sampling from multivariate normal population with large sample size, but unknown sigma. And third one is sampling from multivariate normal population with small sample size and unknown sigma. There are more cases also. Suppose sampling from non-normal population. What is the guarantee that your population will be multivariate normal always? It can be non-normal also. So, it is possible, suppose when you sample from non-normal population, if your sample size is large, because of the benefit obtained from central limit theorem, you can still say that x bar follows multivariate normal distribution and you can proceed. Okay. We will not discuss that part, we are discussing these three scenarios, and let us see that what will happen where your scenario 1 is like this. Scenario 1 is what? Sampling from multivariate normal population with known sigma. This is the case. Now, if you want to know that how they are things are derived in the first scenario, there is one good book which I forgot to tell you in the beginning, that is T. A. Anderson, I think T. R. Anderson or T. A. This one you check, Anderson. This is multivariate data analysis, introduction to multivariate statistical analysis. This is a very good book, earlier than Johnson and Wichern, but the treatment is little different in the sense that it will be difficult for us to follow. So, the first part is available in this book, second and third part is available in Johnson and Wichern. Scenario 2 and scenario 3. So, you write down this one is scenario 3, sampling from multivariate normal population with small sample size and unknown sigma. Scenario 1, the sample statistics is this n x bar minus mu transpose sigma inverse x bar minus mu. Because we know sigma, we straightway use this one, and based on our earlier discussion, all the earlier classes, if you remember, I do not require to write that the sampling distribution will be chi-square, because you all know this, earlier you have seen that this square term will follow chi-square distribution with p degrees of freedom. And what is your 100 into 1 minus alpha % confidence region? This is less than equal to chi square p alpha. This quantity will be less than equal to chi square p alpha, and if I say that probability that this quantity is less than this equal to 1 minus alpha. Okay. See, define steps, define population, identified appropriate sample statistics, find out the sampling distribution, then find out the confidence interval. This is the step. So, for all cases, not necessarily this case, for all cases these are the steps. Okay. Can I go to the next slide? Suppose scenario 2, you are sampling from multivariate normal population, sigma unknown, but your sample size is large. What is the difference here? Difference is simply that if you see this sample statistic, it is almost same to the earlier one, except this quantity S inverse instead of sigma inverse, because now sigma is not known, S is the estimate of sigma. So long your sample size is large, this quantity also follows chi-square distribution, and always the degree of freedom will be the number of variable you have considered in defining the multivariate population. and your probability that n x bar minus mu transpose S inverse x bar minus mu less than equal to chi square p alpha, that will be 1 minus alpha. Now, if I ask you what will be the case for the third scenario, what will be the sample statistics for the third scenario? What is our third scenario? Scenario 3, this one, it is not scenario, it is scenario 3, sampling from multivariate normal population with small sample size and unknown sigma. T square, everything is T square here, this under different situation, but definitely for small sample the T square is known as Hotelling T square. What distribution it will follow? F distribution. Okay, let us see. This is scenario 2, this is scenario 3. So, population is this is the condition, sample statistics remain same as earlier for the scenario 2 and sampling distribution is changed to F from chi-square distribution. And if you know these three, the other thing, the confidence region part is very simple again. So, you will get this one is less than equal to n minus 1 this quantity. Okay. I hope that there will be no problem, at least from confidence region point of view, and you will be able to identify the confidence region properly. And you will also require to little bit, your study is required little bit, where understanding that what distribution you require to use. Okay. This is my example now. So, example 1 we have done lot of calculation using example 1. Example 1 was that what will be the T square. So, I can go to this is my T square. I think it is not visible, now it is visible. So, this is your T square for the example 1. You also have found out that your distribution is this. Then what you require to do, you require to find out what is this value. What is this value? F218, this value is 3.555. As you see here, I checked from the table, you check from the F distribution table, if there is mistake you please correct it, I do not think it is wrong. So, 38 by 18 into 3.55, this is 7.51. Now, this is the T square value, it is less than 7.51. This is my confidence region. In this case, this is the confidence ellipse. I think you will be able to compute. There is nothing great here. It looks very complicated if you see the equations, as if there is something big things, but ultimately the understanding point of view this is not big. But if you say from derivation point of view it is very big, and we are not statistician, we are basically applied engineers, all of us almost, or applied either engineering, basically in the applied sciences we are working, and our aim is to make these complex statistics as simple as possible and then use it, that is the issue. Okay. You want this? You check this calculation also by your own. I think I have to show this, otherwise they will switch over to me that video mode. So, this is 1.33, this point already you have computed this one, now it is less than 7.51, this is the issue, this quantity you will be getting. If you find it difficult, please again come to me, I will tell you. Now, let us go to the second portion, which is also equally important here, because we have done one study in quality control where we found out that several variables are there, and then we have used this confidence ellipse using two variables simultaneously, and we found out that what are the outliers or the out of control observations. We found out something like this, that observation number 5, observation 14, maybe observation 41, these are out of control observations from quality control point of view. How we found out? If we use the confidence ellipse, you will be finding out what are the observation out of control. Now, my question is, 5 is out of control because of x1 or x2. 14 is out of control whether it is both the variable is contributing to this or one variable is contributing to this, like this, that was the starting point what you have thought of. Okay.
It is only one variable, should be 2, no? Should be 5 comma something should be there. Why only 5?
What 5?
When that confidence interval, no? Saying like for the 2 variables, it should be 5 comma a comma b. Like it should be a comma b, only 5.
5 variables we have not taken here. When we are talking about confidence ellipse, 2 variables.
5 what you have shown.
5 I have shown somewhere. Which one?
You have written now.
Oh, that means you have not listened properly. I said this is observations. Observation number 5, observation number 14, observation number 41. Your confidence ellipse is this, let it be, and your 5 is falling here, suppose 14 is falling here, and 41 if I write somewhere here, suppose it is falling here, let it be here itself, no problem. Then these are not falling within my 95% confidence ellipse, CE if I say confidence ellipse. What I am saying here, 5 is out of control, 14 is out of control, 41 is also out of control. You want to know which variable is causing this observation out of control. Is it x1 alone, is it x2 alone, or x1 x2 combiningly, that joint effect is also coming here, that we do not know. That is possible only when you will know this only when you go for simultaneous confidence interval. Now, we will discuss simultaneous confidence interval, how you compute simultaneous confidence interval. Okay. Very important concept, and you will find its application also, and you will be happy to apply this in your project work. What is given here? CR can be visualized pictorially for p greater, cannot be visualized. CR does not give any information for individual variables confidence interval. Simultaneous confidence interval serves the purpose. Two methods of constructing SCI, there one is linear combination approach, other one is Bonferroni approach. There are two approaches, both the approaches are available in the book of Johnson and Wishart. Please go through chapter 5. Chapter 5, and what is this linear combination approach? Let me give you the basic idea here, and then you will be able to compute by your own. If x is multivariate normal, and let A transpose is some constant A1, A2 like AP. Okay. So, A1 to AP, and you have seen the linear combination in last class. I told you that linear combination is A transpose X. Okay. So, now X bar is also your multivariate normal. So, you can create linear combination of X bar also, yes or no. And one of the properties of multivariate normal distribution is the linear combination will be univariate normal. Can you remember? I told you 4 properties of multivariate normal distribution. First one is, if X is multivariate normal, individual variable will be univariate normal. Second one is, subset of that multiple variables will be multivariate normal. Third one is, linear combination of these variables will be univariate normal. So, our X bar is multivariate normal with mu and sigma by n, these are the parameters of the multivariate normal distribution. Then A transpose X will be univariate normal with A transpose mu, that will be the mean value, then A transpose sigma A by n, that will be the covariance, variance in this case. Why variance? Because it is univariate, ultimately this quantity will be 1 cross 1. So, this is the case. Now, if you know this one, can you not create this matrix statistics here? You see here the statistics what we are writing here. Z is the random variable minus expected value of this random variable divided by square root of variance. I think you all have seen this one earlier when you have developed Z. So, if this is the case, then this one A transpose X bar minus A transpose mu, because expected value of A transpose X bar is A transpose mu, it is A transpose expected value of this one is A transpose mu. And also you have seen that variance of A transpose X bar will be A transpose sigma A by n, that you have seen earlier. And as we have taken this quantity A transpose X bar minus A transpose mu, this is your Z distribution.
That one, that A transpose X bar, which is ultimately in second line, second row, NP or N?
NP.
That is the
A transpose, this is N, this is N, not P. This P, that is the cut and paste problem. Okay. So, Z is, because I told you the property says that linear combination will be univariate normal. Now, Z is your that this quantity, if we just derived in this manner, you will be getting this Z distribution which is 0. Now, if you know this quantity is Z distributed, can you not create the interval? If I know something is Z distributed, all of you know that minus Z alpha by 2 less than equal to Z less than equal to Z alpha by 2. That is what we have seen in univariate case. This is my Z alpha by 2, this is my minus Z alpha by 2, and this Z will be 0 definitely. Then you put the Z value here. So, minus Z alpha by 2 less than equal to A transpose X bar minus A transpose mu divided by square root of A transpose sigma A by n, this will be less than equal to Z alpha by 2. So, if you further just mathematical manipulation you do, what you will get here, A transpose x bar minus z alpha by 2 square root of A transpose sigma A by n less than equal to A transpose mu less than equal to z alpha by 2 plus, write down A transpose x bar plus z alpha by 2 square root of A transpose this by n. What will happen if I choose A equal to all 0, 0, then jth element will be 1 and then 0, 0 like this. What is this? This is 1 cross p, this is the transpose 1 cross p. What I am doing, the first constant is 0, second constant 0, only the jth one is 1. If you put this into here in this equation, what you will get? You will get like this, x bar j minus z alpha by 2 root over s j j by n sum less than equal to mu j less than equal to x j bar plus z alpha by 2 square root of s j j by n. Getting me? But there is a problem. What is the problem? Problem is, see, if you see this equation, in this equation it is just like a univariate confidence interval, because we have noted j only. If I do not write j the way we have defined in univariate case, we have written x bar minus z alpha by 2, then your s by root n less than equal to your mu less than equal to x bar plus z alpha by 2 s by root n. There is no difference between these two. If there is no difference, then ultimately where you are landing now? You are going back to this, you are going back to individual interval a b for x 1 bar, that is for mu 1, and your a d for mu 2. If I go by this method, what will happen ultimately? Your problem lies here. Problem is, suppose you want 100 into 1 minus alpha percent confidence interval. When there is one variable, you are getting like this. When there is two variable, again you are getting this. So, second one 100% CI. So, like this, if there are 10 variables, what will happen ultimately? You will get 1 minus 100 to the power 10% CSI, considering that all independently you are estimating the CSI. So, if your alpha is 0. Suppose 10, then it is 0.9 to the power, even for the two variable case it will be 0.81. So, 81% simultaneous interval you are getting, confidence interval. You will not get 95% or here 90% what you thought of. So, you require to rectify this. If you go by linear combination, you require to rectify this. That rectification mathematics is also available in Johnson and Wichern. In chapter 2, you go to the matrix algebra portion, you will be finding out there is one beautiful concept called maximization lemma. It is coming from matrix algebra. Okay. What is this maximization lemma? Is this. So, my work is to simplify this and tell you that 2-3 pages write up you will be getting full of that a x bar mu sigma like this. So, do not worry while reading this one, but you please remember that this is what, that for non-zero A, that the maximum value of A transpose x bar minus mu square by this is nothing but the z, this one A transpose x bar minus mu by A transpose sigma A by n, that square root is z, the square root square. So, that is z square. Okay. So, z square follow this quantity, z square will be this. Now, all of you know what is the distribution of this. What is the distribution of this? Chi-square distribution. So, we will in next class we will discuss this one, we will continue. Okay.